Hey guys, welcome to another AI Tech Talk. In this video, we're going to be going over decision tree classification with weighted samples from Scratch in Python. This is going to be useful in algorithms such as AdaBoost and others that use decision trees with weighted samples. This Tech Talk assumes you watch decision tree classification with weighted samples. It also assumes you have seen gradient boost regression from Scratch, sklearn style. If not, check out the talks. So let's get started. We first import the necessary libraries used, including NumPy and Graphviz, because we plot the binary tree at the end in a graph structure. We're just going to use scikit-learn's make classification function because that generates a two-class classification problem using a cluster of points with a normal distribution with it. We get a data set with 4 features and 1,300 samples and shuffle it. We can then create a random permutation of integers from 0 to 1,300. We use this to define our training index and testing index by taking 80% of the training set and the rest for the test set. We then use fancy indexing to define the feature set with xtrain and xtest, as well as the labels with ytrain and ytest. We can then use our self-referential node class here with an info dictionary and a left and right node variable. The decision tree classifier class is essentially the same as the regressor class, with the min sample split as the number of samples to split a node and the weighted impurity decrease as the impurity of the parent node minus the weighted impurity of the right and left children. In the decision tree with weighted samples video, I describe how the NTR and NTL values here are the sums of the sample weights instead of the number of samples in the node. In the build tree function, we pass the feature set X and labels Y with a current depth of 1. If the number of samples in X is greater than the minimum number of samples in a node, then we call the get best split method with the current data set. Next, we check that the impurity of the split is greater than the minimum impurity decrease. Here, we just use a minimum impurity decrease of 0, but can pass in any value to the constructor. In the if statement, a left bool array is set to define a Boolean array of the samples that have the feature less than the threshold. We then use Boolean indexing to split the dataset into the left and right halves. We take x sub left bool directly, but since the label array y is set differently, we have to access both elements of the list. The way the code is set up is y is a list containing 2 elements, with the first as the normal label array and the second as the sample weights for the labels. Thus, we have to access each element of the list to use Boolean indexing on each element. The first element is the label array and the second is the sample weights. We do the same thing with the right half of the data set, and then we call a recursive function on the left and right child to build the tree. If we hit a leaf node, then we save the labels and sample weight lists in the values key of the best split dictionary and return the node. Now, to find the best possible split with the largest impurity decrease, we use our get best split function and pass the feature set X and labels Y. We loop through all features in the dataset and all possible values or thresholds in each feature. We again define a left bool array as a Boolean array of the samples with the feature less than the current threshold as true. The Boolean array is applied to each the class label array and the sample weight array to split the data into the left and right halves. Then, if the sample weight is greater than the minimum number of samples, we define the parameters for the weighted impurity decrease by summing each of the sample weights for the parent samples and the left and right constituents. Finally, we can apply the weighted impurity decrease formula by calling the Genie method and checking if the impurity decrease is greater than the previous iterations. The Genie method is a simple function that obtains the unique values of the class labels. It then goes through each class and calculates the probability of each class in the node by summing each sample weight of that class and dividing by the total sum of weights. Then we apply the Genie index formula and multiply the probas by 1 minus the probas and sum the result. For the fit method, we have to pass the feature matrix and target labels as well as the weights of each sample. If the sample weight is not passed, the default value of none is set. Here, if a value is passed, we set the instance variable to that sample weight, else we set each weight to the normalized value. We then define the modified target array to include the sample weights in the second element of the list. The make prediction method is the same as before, where a prediction is computed for a single observation in the dataset. In the predict method, however, we cannot just take the class that appears the most in the leaf node. We have to call the predict prob method and obtain the weighted class probabilities and then apply the argmax to get the index of the highest probability. So for the predict prob method, we have to calculate the probability as the weighted proportion of samples of the same class for each sample and each class of the dataset. A probas array is defined to have a 2D shape of the rows as each sample and column as each class. We then loop over each sample in the dataset and call the make prediction method to obtain the labels and weights for the sample. Then we loop over each class in the dataset and calculate the probability as the weighted sum of all the samples in that class divided by the total weight of the leaf node. Then we return the result and can get the weighted probabilities for each class. So let's go ahead and run the decision tree classifier with equal sample weights and see what we get for a depth of 5. Let's also run a tree with different sample weights to see if it will be different than having just equal weights. After running the program, we see that we get a good accuracy of 89% for equal sample weights and 87% for unequal weights. As always, we run the save tree method to save the decision tree in a graphviz format and use that function for both of the trees created. Now we can see that the decision and leaf nodes are different for each tree with equal and unequal sample weights. So that's it for this Tech Talk, guys. If you liked the video, please support the channel by subscribing and sharing with your friends.